Hello, good morning to everybody. As a president of this academy, I'm very happy to welcome all of you in this prestigious venue. Probably some of you knows, but most of you probably do not know that the Academy of Sciences of Bologna has been founded more than 3 centuries ago at the end of the 17th century. And since its foundation, the site where all the meetings of the academy were held is this building. And the academy is in this building before the University of Bologna. You know that this building, Palazzo Poggi, is the venue also of the University of Bologna, which is here since the beginning of the 19th century. So the Academy of Sciences has this important task in the city of Bologna, but not only in the city of Bologna, to promote the science, the physical sciences, chemistry, physics, medicine, biology, and so. And since the beginning of the 19th century, also the humanistic sciences, literature, history, philosophy, and so on. Now, this morning is the time of chemistry, and we have the pleasure to host here a very famous professor, Paul Anastas, who will receive the Laurea ad Honorem from our university. And we are very happy that he has accepted also to participate at this round table on the topic, which is the topic of Paul, future green chemistry, the achievements, the challenges, and the perspectives. And this is a panel discussion with some professor of the University of Bologna, but not only of the University of Bologna, also from other universities. And the chairperson, as you see from the program, are Paola Galletti and Emilio Tagliavini. I also thank other persons who have participated to the organization of this meeting. I hope that persons who do not know the city of Bologna, I realize that for Professor Anastas, it's the first time in Bologna. So I also hope that he will enjoy the city, which can offer many possibilities of interest, not only for eating, but also for appreciating architecture and art. And Bologna is a small town, but is famous in the world because all people who arrive in Bologna appreciate very much the humanity of Bologna and the humanity of the citizens of Bologna. So I again welcome of you. I wish you a fruitful meeting and a fruitful stay in Bologna. And thank you again for coming here. Good morning.
Now I invite Professor Marco Lucarini, who is the head of the Department of Chemistry.
Thank you, Emilio. So for me, it's a really great pleasure on the behalf of the chemistry department, Giacomo Ciamician, to welcome you, to welcome everybody to this event. In particular, I want to thank Professor Paul Anastas for being here. I can say that it's truly a reason of a great honor to have the father of the modern Greek chemistry as our guest. I know that this week will be very long, very demanding for you, but this is a really great opportunity for our colleagues, for our students to talk with you. So once again, thank you very much for your time. I want also to thank Professor Bolondi for having hosting this event. I want to thank all the speakers. Thank you very much for accepting our invitation. And also I want to thank Emilio and Paola for having organized this event. So I don't want to waste your time more. Thank you very much, Paul, for being here, and thank you to everybody, and have a nice day. Thank you.
Thank you, everybody. So I welcome you all. I'm Emilio Tagliavini, an organic chemist from the Department of Chemistry of the University of Bologna. We are organizing this event to have the opportunity to take some time and have a discussion with Paul Anastas, who is here for this week. And we start introducing the speakers. I will share my chair with Paola Galletti. We have shared many things in the years since more than 15 hours ago, we started to make some green chemistry in the University of Bologna, and this is a passion for both, and this is the reason why we are here today. So we start with Paul Thomas Anastas, who is Teresa and John Haynes' third professor in the practice of chemistry for the environment and director of the Center for Green Chemistry and Green Engineering at the Yale University in Connecticut, US. We will say only a few words about Paul because his CV is very, very long. It will take all the day to acknowledge everything about him. He's university reputed the scientist who gave birth and brought to growth the green chemistry. The probably most famous achievement is in 1998, the creation of the 12 principles, together with John Warner in a famous book. But he started before to boost the green chemistry, and he was the promoter of the establishment of the Presidential Green Chemistry Challenge Award that has been a standard for the improvement of green chemistry. Paul has been also the director of the US Green Chemistry Program at APA. Yesterday evening, he said that he spent half of his career in institutions and half of his career in academia. He also served as director of the American Chemical Society Green Chemistry Institute, and he served as assistant director for science in the White House with many US presidents. He is engaged in many programs on sustainability and green chemistry, and recently he launched the Global Green Chem Accelerator Network with the United Nations. He's also an important researcher. He co-authored more than 200 papers and 15 books in the field of chemical sustainability. His research is on many topics: renewable energy storage, carbon dioxide utilization, synthetic method to transform bio-based feedstock, molecular design for reduced toxicity. We must recognize the guidelines and the ideas of Paul Anastas have been source of inspiration for a couple of generations of young chemists and innovative entrepreneurs. For all these merits, Paul Anastas will be awarded the Laurea Honorem in Chemistry by the University of Bologna on next Friday, and we hope that you will join this event. Then we have other very outstanding panelists. One of them is Giulia Licini, who is full professor of organic chemistry at the Department of Chemical Sciences in the University of Padova, where she's in staff since 1990. She obtained a PhD with Professor Giorgio Modena that we all remember. And then she's been postdoc fellow at the Colorado State University in Fort Collins with Professor Albert Meyers. Now she holds the chair of the interdivisional group of green and sustainable chemistry from 2022 of the Italian Chemical Society, and she's in the board of the Division of Organic Chemistry of the Italian Chemical Society, and corresponding fellow of the Galilean Academy of Sciences. We always remember that Padova is the University of Galileo Galilei. Academy of Sciences, Art and Letters in Padova. Her scientific contribution focused on the development of new transition metal catalysts for small molecules activation, H2O2, oxygen, and so on, and stereoselective processes. But more recently, she has been attracted also by the catalytic aerobic oxidation of biomass, the activation of CO2 to produce cyclic carbonates. She co-authored more than 130 scientific papers. Now I give the stage to Paola.
Screen. Okay, good morning to everybody. Thank you for being here. I also welcome the people that are connected online. And I will go to introduce the other three panelists, starting with Fabrizio Cavani. Fabrizio Cavani obtained his PhD in industrial chemistry in 1987. He was then hired by Honorem Synthesis. They're now the industrial part of our roundtable, and began working at the Catalyst Center in Sesto San Giovanni. During this period, he carried out research activities in the field of catalyst and mixed liquid gas phase reaction that I think is still one of his main interests. Is still a keyword of all his research interest. Then he joined the University of Bologna as a researcher in 1990, and now is full professor at the Department of Industrial Chemistry, Toso Montanari, here in Bologna. Then is a member of the advisory board of the RSC journal Green Chemistry, of the Chems to Schem journal of Wiley, is president of the divisional catalysis group of this Italian Chemical Society, member of directors of the Industrial Chemistry Division of the Italian Chemical Society, and he belongs to the board of FCAPS, the European Federation of Catalysis Societies. As for the number of publications and patents, I won't tell the number, it's huge, but what is more important, it is that many of them has reached the industrial development. Then going on with the industrial part, let's say, of our roundtable, I'm pleased to introduce to you Luigi Capuzzi, that graduated in chemistry from the University of Perugia in 1981 and began his professional career as a researcher at the Guido Donegani Institute of the Montedison Group, dealing with the synthesis of pheromones, of new insecticides, and in the development of new agrochemical formulation. Then in 1995, he joined the SIPCAM Oxon group, where he was responsible for the group's research and development and director of the Gagliardini research unit until 2008. Since 2008, he has joined Novamont as with the role of director of research and development. You all know that Novamont is a leading international company in the bioplastics and biochemical sectors. He is co-author of more than 50 international patents, and so also in this case, in patents application, as well as several publication and communication. Our final finalist is Walter Cabri, that graduated in chemistry in 1985 in Milan. Then he spent a period in an ASEAN group in Montreal, and then he started his quite long career in industries, pharmaceutical industries of all sizes, let's say, small, medium, large. I can name some, but please, if I forget something, Pharmacia, Bristol Myers Squibb, Fresenius Kabi, Sigma Tau, Antibioticos, Di Pharma, Indena, and now is still collaborating with Fresenius Kabi. In those companies, he was often the research and development responsible, but also dealt with all part of the drug discovery process. Then in 2019, he joined the alma mater studiorum, University of Bologna, as full professor of organic chemistry in the chemistry department, Giacomo Ciamician. The main area of his interest are still molecules, peptides using enzymatic and homogeneous organometallic catalysis. And in recent years, he really is interested in pharmaceutical green chemistry. And so this is also one of the reasons is today with us. Okay, as for the program, as you see, our panelists will introduce 5 key points of the general topic of this roundtable. The general topic is future green chemistry, achievements, challenges, and perspectives. But then we will focus on 5 specific topics that our panelists will introduce, and then a discussion will follow just after the introduction and also at the conclusion of this roundtable. Then we will have a coffee break for sure, and then we will have a lunch, a buffet lunch at the chemistry department Giacomo Ciamician, which is a few minutes from here. Sorry. For all the organization and also the coffee break and lunches and all this, I want to thank the chemistry department Giacomo Ciamician, the C3 chemical catalysis group, and for sure Accademia delle Scienze. Okay, yes, okay, the chemistry department Giacomo Ciamician through the project di eccellenza, dei dipartimenti di eccellenza. Okay, I guess we can start.
Okay, so thank you, Paola. So we can start our program, our scientific program. And we remember that it is 25 years that thanks to Paul Anastas, green chemistry started and was put to the attention of scientists. So now we can ask what is the progress of this revolution that started 25 years ago in the society of the 21st century. Paul will introduce this topic.
I guess we'll get the slides called up. As I just wanted to say how large of an honor it is to be here. I just want to first, of course, thank Emilio and Paola for this session. I want to say what a pleasure it is to be with so many old friends and so many new friends. And I also want to thank the department and the Academy for having me here. Genuine pleasure. But I would like to also remember a friend who's not here. Pietro Tundo introduced me to Italy and introduced me to so many of you. I am just so thankful to have had him as a friend, and I think we've all, he was always quite a character, and he made such an important contribution. So as I was preparing for this morning, I asked Emilio, well, how long should I speak? And he said, well, remember Socrates. I said, oh, what about Socrates? He said, Socrates could speak elegantly and eloquently for hours and days, and they killed him. So I will be brief this morning. I want to talk about the subject that I enjoy talking about most of all, which is that of green chemistry, sustainability, about where we are, where we're going, where we came from. And I want to reflect that in the over 25 years since the 12 principles of green chemistry were first put out to the scientific world, something that I believe has become clear is that the 12 principles of green chemistry are extremely obvious. So when we look through the 12 principles of green chemistry and we talk about preventing waste and using catalysis, and we talk about energy and atom economy and all of those things, all of us, I believe, would agree that they are extremely obvious. So why did they make such a large impact? Because they were obvious but not done. They had no relationship, almost no relationship at all, to how things were being done for almost 200 years in chemistry at scale. And so I think that we collectively as a chemistry community came together to think differently, to ask different questions about our chemistry and what was possible. Whew, that was startling. Now, there was something that came together yesterday in across the United States. Some of you may have heard about it. It was a total solar eclipse. My daughter happens to be an apprentice to a photographer, and so they went to the perfect spot to witness this solar eclipse. This was yesterday. This was right out of the camera. It is magnificent. And it's even more magnificent when you zoom in. Yes, those are solar flares that you can never see. And it's just beautiful and breathtaking. And yes, I am very proud of my daughter. But it's beautiful and breathtaking because of what it represents is an alignment. This is an alignment, right? It only happens because of that perfect alignment. Colleague who you may know, a brilliant astrophysicist, Neil deGrasse Tyson, said, "We have the best eclipses in the whole solar system." Because even those other planets that have moons, they have tiny little moons and they don't work. It's not a good solar eclipse. We have the best eclipses because the moon is 400 times smaller than the sun, and it's 400 times closer than the sun. And because of that, we have this kind of beautiful alignment. And what I like to imagine is that when we look back over the past 25 years, there is so much beautiful alignment in our chemistry community of imagining what's possible in our various synthetic methodologies, how we choose our feedstocks, how we do analysis, the questions we ask, the goals that we seek to achieve, the ways that we measure success and productivity and efficacy rather than just efficiency. So as we go to this green chemistry, this was published just a few years ago, reflecting on all of the achievements of green chemistry, of the field of green chemistry. It was meant to emphasize a very important point, that as we pursue the chemistry of sustainability, it is absolutely essential that we remember it is not the science of what you cannot do, what you have to stop doing, what you have to minimize, what you have to ban, what you have to eliminate. No, it is not the chemistry of what you can't do. It is what the chemistry of what you can do, what you can create, what you can invent, what you can discover, what you can innovate. And all of these leaves represent a new technology platform, whole fields that have either been discovered or developed, that have expanded, that have created new molecules, new methodologies, new approaches. And yes, in some cases, one could say new industry sectors, because each of these leaves is about that creation. Now, if I were to say these are wonderful academic achievements, that would be true. If I were to say that they are filling up the journals, not just the green chemistry journals, but our great scientific journals with new discoveries and new papers, such as from our friend Professor Truffiero, that would be true. But that would be one small piece. It is because if I were to suggest that they cut across industry sectors from pharmaceuticals to plastics to energy to food to cleaners to personal care and beyond, that would be a bold statement. The bold statement, though, is the fact that they already have these green chemistry inventions, these green chemistry innovations are already in all of these sectors and so much more. So what is the challenge? If we are seeing these in all of these sectors and more, what is the challenge? It's because they are not yet systematically included. They are not yet the rule, they are still the exception. They still have to overcome inertia. They still have to overcome decades, in some cases a century, of embedded infrastructure, even when they are more efficient, effective, higher performance, higher functionality. So what is the pivot that we need to move toward? Just a few years ago, during the pandemic, science asked myself and three of my closest colleagues, Professor Walter Leitner at the Max Planck Institute, Hanno Arithropel, who's a senior researcher at Yale, and my closest of colleagues, Professor Giulia Zimmerman, who's also the vice provost of Yale University for Planetary Solutions. I say my closest colleague because we have two major projects together. They are called our daughters. Yes, Giulia and I are married. We wrote this paper called Designing for a Green Chemistry Future. And this paper outlined a simple process for how we think differently about the way that we generate products and processes, the questions that we have to have asked and answered so that we make substances that are healthful rather than toxic, restorative rather than degrading, renewable rather than depleting. As we know, still today, our chemical sector is largely linear, and that our future sector needs to be largely circular in many different ways. But it's not just simply the circularity, and just a quick pause on circularity. It is oh so crucial that we get circularity right. Because there are many hard questions, there are many hard tasks to take circularity from an elegant concept into a genuine beneficial reality. The science that is needed, the green chemistry that is needed to make circularity real and beneficial is not yet in place, and we need to have that very deep discussion and a lot of work on that. So it's not simply circularity. But these are really, in so many ways, the majority of the transitions that we need to move from today's processes, which are still overwhelmingly fossil-based, to renewable-based. We know that the So many of our reagents are reactive, persistent, and toxic, and they need to be designed to be benign. When we look at catalysis, the evolution of catalysis, moving from rare precious metals to earth abundant metals, base metals, enzymes. And yes, the future, and I say this in Bologna, needs to be photons and electrons. I say it with so much humility because of the wonderful history. Yes, the future needs to be photons and electrons. We have spent 200 years mastering the covalent bond. And yet, would any of us say that we have the same mastery of weak force interactions as a design tool? And yet at the same time, we know that our greatest teacher, our greatest mentor, our greatest design partner, nature, uses weak force interactions to get so much of its functional performance. We know that we need to move away from our traditional solvents to low toxicity, recyclable, or even solventless systems. We know that we need to move away from the dominance of separations with all of its energy and material waste into how we thoughtfully design for self-separating systems. When we start thinking about waste, we need to, of course, always think about step and economical approaches, but most importantly, it is going to be important to think in terms of systems. We will need to look across the systems rather than optimization of unit processes, step processes, and recognize that interconnectivity will be essential. Ideally, we need to define performance, not as simply a narrowly defined specific goal or yield or conversion or Faradaic efficiency, but rather how we get all of those traditional functions as well as reducing or eliminating hazards to human health of the environment. I'll just finish by saying all of those challenges are extremely difficult, but worthy, because it's what we must do. And one of my favorite quotes that Robert F. Kennedy used to use is, "Some see things as they are and ask why. Others dream of a world as it could be and ask why not." All of those challenges, all of those necessary challenges are possible. So why not? Thank you.
Thank you, Paul. Now we open discussion and we start with Giulia, if she wants to add something to what Paul said or to introduce something about this topic.
Okay, thank you very much. It's really, as usual, inspiring. Okay, I will tell something about also later, but I would say, okay, why not, for sure. But sometimes the approach is very complex. And I think the difficulty that we can have is really to merge all these different approach that of course with the 12 principles we know and we try to apply. So I think, yeah, yeah, it's complicated. Beside the fact that we agree totally that we have to move in this direction, and because of the future, not only because it's challenging as a scientist, of course.
If I may.
Yeah, if you want, you can reply.
Oh, just, I completely agree with you that this is a very difficult and very intricate system. What I will say is I would ask do we think it's complicated or do we think it's complex?
Complex.
Yeah, and so I would say you're 100% right. I think it's a very, very complex, and none of us went into chemistry because it was easy, right? And so we like a challenge. Thank you.
Okay. So Walter, do you want to add something to what we?
No, of course. I mean, we all agree with the presentation and what we are talking about. One of the key elements that we have nowadays, of course, is globalization. In the, let me say, Europe, US environment is complex, can be done. Worldwide, I think that's the challenge. DDT is banned almost everywhere, but still India is producing 10,000 tons, China 4,500 tons, North Korea as well. So there's still 3 countries that are producing DDT that has been banned in Europe and US since a long time. So I think that in addition to the complexity, the key point here is what are we going to do globally? And I think you are in some way involved in this kind of global approach, because that is what is missed still, from my point of view.
Okay, of course you are free to intervene, to talk when you want. Now I pass the word for the same topic to Fabrizio. Do you want to add something?
I would like to add a point concerning the economics. I mean, everything is beautiful, fine, but everything costs, and not always companies are willing to put the money and invest in order to develop new technologies. And moreover, you have to take into account that not always the society is ready to pay more for something which is done or synthesized by means of green chemistry. I mean that typically I used to ask to the people who is willing to pay 50% more for something which is done from renewables, and no one is raising the hand. Okay. When I ask, okay, at least 20%, no one is raising the hand. Finally, when I say, okay, who is willing to pay 5% more because something is done in a greener way and not from petroleum, for example, and maybe someone is raising the hand. So finally, someone has to pay the difference. And this, I think, is the main problem today.
My friend. So I recognize what you're saying, and is it a problem? I'm going to ask a question of the audience, maybe a few questions. If you could raise your hands, how many of you know that climate change is real? Thank you, thank you. How many know that biodiversity loss is real? Thank you. Sadly, I asked this with somberness. How many of you know that cancer is real? Okay. Now, I ask one more question. How many of you know that money is a shared fantasy? Why? Why would we be making decisions on all of these very real things, some of them existential threats, based on a shared fantasy? So what do I mean by that? Because you can say, oh, well, money seems real to me. You know, it has real consequences. No, I'm talking about things that exist whether or not we agree on it, right? Whether or not we share, okay, this little piece of paper or this little plastic card has value. No. When it doesn't take humans to agree on it, that's real, right? So when we step back and we take a look at some of the economic challenges that I completely agree with your characterization of the real world, right? We look at the fact that there is extremely little consequence, economic consequence, for causing harm. So if I were to tell you that globally, the the fossil fuel industry is being subsidized at $11 million. You'd say, if I were to tell you that it's $11 million every minute, you'd say, oh my goodness. So when we start thinking about the economics of disruptive technologies, of new startup companies, and new technologies trying to get it started, my goodness, some of those little companies would love to have a minute or two of that funding, wouldn't they? But if we ask ourselves, what is the real economics? Because I would suggest that our market systems, the equation is we are privatizing gains and socializing losses. So I will ask you, if we talk about biofuels or biomaterials or whatever it is, $11 million a minute? Are fossil fuels economically viable? Are they really, or is it just a contrivance? Because that $11 million a minute has been going on for over a century. So next time we talk about economics, we really need to think about, well, this is not economically viable. And say, economically viable to whom? Economically viable for whom? Because I'll finish with this, because I know this is a long response. If suddenly we were to see a new invented technology, and this is $1 trillion technology that has just been invented. Now, if that $1 trillion technology will make $1 billion each for each of 1,000 investors, that technology will happen. It will be invested in, it will be commercialized, and it will go to scale. If that $1 trillion technology gives $1,000 worth of value for 1 billion people on the planet, that technology is probably never going to be invested in and never come to scale. And yet, today in this world, perhaps the most important transformative technologies are those that bring a billion people $1,000 worth of value, whether it's in food or water or energy.
Okay, so Luigi, do you want to add something about this?
It is quite difficult to add something. I've been particularly interested to the concept that we need to transform circularity from an elegant concept to reality. This is, and I think that one way to obtain this objective is not limiting us to ask how to realize a new product, a new object, but also ask to us why we need to make some kind of object. For example, we have a lot of objects that we use. Most of them or part of them are maybe useless. And so from my point of view, it will be not sufficient, let me say, to transform the raw material to make an object from fossil to renewable, because if I will, let me say, follow the same approach with renewables that we have used for fossil in the past decades, maybe we will do also worse, and we will have also worse consequences if we will follow the same approach. So we have to change the paradigm, and obviously I completely agree with the idea to make circularity something real. And this is what we are trying to do in our company. So thank you for express this concept in a very, very clear way.
Thank you. In a very brief response, thank you. I appreciate that. I just wanted to say that with regard to circularity, if we were to say, let's implement circularity today, that would implicitly be stating that we think that the material basis of our society and our economy is optimized, that we want to keep those materials in the flow. I don't know of anybody who believes that. I don't believe that anybody who says, yes, the materials that we use today are the ones that we want to keep in. So we need to envision how circularity allows for innovation and allows for new materials in and and undesirable materials to phase out. Because if we insist on absolutist circularity, we will put the innovations at a disadvantage and we will lock in undesirable materials. So we just have to be thoughtful about our policies, about how we integrate that, how we incorporate that. And I have to confess, I'm not seeing that in the discussions yet on the policies around circularity. And I hope we do. So, thank you.
Thank you. So are there questions from or observations from people here? Claudio, Ferruccio?
So thank you, Paul. I have first a comment. You asked us, do you know what is climate change? Do you perceive what is it, or the loss of biodiversity? But we have to remember that half of the world is in the hands of right-wing leaders who are deniers of all this. But I will come to a more specific problem of green chemistry. I will speak about solvents. I read now in the internet that the global market production is in the more or less 30 million tons production of solvent per year in the last year. The business is $20 billion, I think, per year. 50% of all the production is directed to the sector of paints and coatings. Well, when I was thinking, when we paint a wall, or a car, a fabric, something, the solvent leaves, the system dries, and the solvent goes to the atmosphere. How can we remediate this? It's very difficult. So do we have an idea and a suggestion for that?
So, yes. So, and this comes back to the comment about nature being our greatest teacher. So what we're talking about is getting functionality, getting performance of how we accomplish particular functions, right? Now, of course, we have the solvents we have because we have the feedstocks we have. The fact that we have a hydrocarbon-based economy means that we have used these hydrocarbons and organohalogenated solvents in order to now, and we know water is the universal solvent that nature uses, right? And why is that? Because of the nature of its feedstocks, highly oxygenated, highly polar, able to be. So when we talk about solvent systems, it is a system. So what we're trying to do is dissolve, diffuse, isolate, clean, and in the case that you mentioned, evaporate. Now, what we're looking for is a nice smooth coating, for instance, right? For a paint or a coating. Now, is dissolution and evaporation the only way to achieve that? I'm guessing everybody will say no. We can achieve that function in other ways. It can be through molecular self-assembly. It can be through vapor phase deposition. It can be through other mechanisms. So looking at how we accomplish, smoothness, hardness, looking toward nature, and whether it's looking at seashells or whatever you want to look at, is usually a good place to start. The other thing that I'd say is so very, very much, and I might talk about this on Thursday too, of our use of solvents is because, I'll just say, we need separations to achieve purity. And yet, while we aspire to purity, everything in nature is a mixture. We have no mastery of mixtures, none. When we start thinking of how you get performance and control, we think about purity. Purity is essential for control. But we've never outperformed nature yet, and everything in nature is a mixture. I think we got some learning to do.
Professor Trifiro?
So when you started to use green chemistry, the word green chemistry, for me the meaning was don't use a toxic substance. But now we use sustainable chemistry. Is correct to call sustainable chemistry green chemistry, or green chemistry is only a part of sustainable chemistry? What do you think?
Well, something that I truly believe is, while I know the definition of green chemistry, because it's 21 words, green chemistry is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances, period, full stop. If you ask me the definition of sustainable chemistry, I can probably give you 2 or 3 dozen definitions, but I can't give you one. So I don't necessarily know what sustainable chemistry means because it means so many things to so many people. But a couple of years ago, we wrote a tribute to the periodic table called the Periodic Table of Green and Sustainable Chemistry. And I might talk about that later in the week. But the point was that I genuinely know that you can't do sustainable chemistry without doing green chemistry. In the same way that you can't bake a delicious cake using spoiled eggs or rotten milk, you have to start with the inherent nature of your molecules and your materials being inherently benign by design in order to achieve anything that you're going to describe as sustainable chemistry.
Other questions from someone?
Hi, thank you for the presentation. And I would ask you, nature is had in research and development for quite a few billion years. And how could we close that gap? And would you think that the use of AI would be useful?
Well, I completely agree with you. Nature has 3.8 billion year head start on us. Would be wise to do it. How do we go about doing it, and can we use AI? Well, I think we start with humility and recognize that every time, we're not so bad at speeding things up. I think we should be really proud of the fact that we can take processes that happen in nature and speed them up, and we should pat ourselves on the head and recognize the power of catalysis, because it'll be absolutely essential. But in terms of directionality, I'll often say that the compass is far more important than the speedometer. So recognizing that we have to get the character and the nature right, and so learning from nature about how it carries out transformation, how it gets function and performance, using that as a lead. When asking about AI, I think that from what I've been seeing, there's perhaps nothing better than good AI and nothing worse than bad. But it's a longer conversation, Thanks.
Okay, thank you. Of course, the other panelists can add something if they want. Otherwise, there are no questions online in chat, I suppose. Okay,
Just a final comment, if I can. And another sentence that I love very much that comes from green chemistry is benign by design, which is, I think, a way to collect several inputs that already come from this discussion, because we have to start in a new way to think about innovation, not to repeat, let's say, in a greener way what we are used to do. So benign by design is another point that I like very much. Okay.
Okay, so now we can pass to another topic, the same topic, but from another point of view. The revolution of green chemistry has provided tools to scientists, industrial and academic scientists, and now we want to talk about these tools, and Giulia will introduce this topic.
Thank you very much. Okay, before starting, I really want to thank Emilio and Paola for the invitation, and also the Marco Lucarini for hosting organizing the day. And yeah, okay, this was a topic that they proposed to me. And so this is, no, I would say, and it's very nice because usually you think a little bit more. If you choose the topic, something that is with you, otherwise you have to think a little bit and just focus what it is and which is your view, of course. So as a chemical scientist, I'm an academic chemical science, so I would say I will talk more from our point of view as academy, because then the industrial part will be more, let's say, there will be much more, contribution. And then as a scientist that is really fascinated by green chemistry, is the question is, how do I green up what I'm doing, or how I can do something in a greener way? And so usually the normal approach is just I change the solvent, I use alternative solvents, all the, let's say, the paradigm that we learn out of the 12 principle of green chemistry. So I can use, move to flow chemistry and so on. And as I said before, this is important, but certainly is just a piece, is very sectorial, is partial by nature. And so how can the green chemistry community can help the researcher wants to be active in this field and do something new, not only to green the process? And I might say I took really inspiration. No, how do I go this way? Okay, this is a certain contribution of Paul Anastas as well, from the from the American Chemical Society, the Green Chemistry Institutes. And there is a very, very nice contribution that points out the different aspects that we can look at in a different way. And these are, of course, is always related to the green chemistry principle, but it is really to have these tools in order to work more efficiently and create something new. And beside all this, I just listed some of the topics that are treated in the homepage, in the web page. And in each of these, of course, it's very limited, but there are the focus principles, some very interesting example, and some very important literature. So I'm pointing, I'm looking with the eyes maybe of a young researcher that wants to face the field and maybe find inspiration. But beside this, there was there's one part that is really related to green chemistry research tools. And I will say I have been always very impressed by this effort, because it's, as I said before, is a lot of different things that should merge in order to find a solution, or to start already from a point where you take advantage of the knowledge and you can develop something new. And beside all the metrics and so, they sometimes are very difficult to apply. So you do that, or you do another things, but they are, of course, also when we teach, those is not very, very straightforward and easy. And I would say all these different topics have been developed in a very impressive way with the help of roundtables of different companies, especially pharmaceutical companies, because maybe for the kind of research that I'm doing, of course, the research in a pharmaceutical company is much closer, because you have solvent, you have homogeneous reagent, and so on. But that's the typical. And I would say, I just took an example. Of course, I've been doing oxidation for a long time. And this Venn diagram is very, very inspiring because they put what your idea already in, inside this circle, because you are already doing something interesting, but in the center, let's say you have the merge of the scalability, potential scalability, the wider utilization, and then utility and the greenness of your process. And I think the example that are given is very useful. Is easy to use. You have very brief, of course, information that this was epoxidation, and in particular, I think I choose with metal and hydrogen peroxide or whatever. But it's really in the view of green chemistry. This is an effort, at least on the page, was written of many, many hours of work. So it's work based on the literature, based on research, extract by a group of people that have been working on this. But this is effort, I think, is not only the tool, but is a way to take advantage of the tool and just put what we do in a green chemistry view in order to not to make mistake, to lose time in doing things that maybe are already out of the circle and will be not useful. So as let's say, a chemist in research, I think an effort of the chemical society, or of course, there is a big input from industry, of course. So it's extremely important. And because give you the direction. And then there will be your creativity, your new ideas, the development of new things. That is a privilege of the academy. Sometimes we are not, we have a little bit of bound, but not so many as in any industry where real things are made, by the way. And the second tool, I say is a little bit a long step. I would say is education. In my, let's say, last part of my career, I've been really much more involved in education, and I believe that is extremely important. Maybe in academy, one is our second goal, but it's a very, very important goal. And this is also something that American Chemical Society, the Green Chemistry Institute is doing, at least for what I saw. And what everyone should do is just to bring the green chemistry concept in the basic courses of our students. The other day, I was teaching oxidation of alcohols with chromium. Okay, there's a stoichiometric process, so I feel bad, but okay, this should be stopped. No, those kind of, even though the mechanisms are easy, they understand, but it's totally wrong. So, but this is in every book, textbook. So really, we should, all of us, use this tool, because it's not only a tool, because if the new generation grow up with this idea, they will find better solution. Maybe, also for what I was saying, I don't know if artificial intelligence will help in put things together and grow up these tools faster instead. But it's certainly, okay, for the education, not only a tool, but certainly a goal. So thank you very much. And I hope that I can make some input.
Thank you, Giulia, for this inspiring words. And now we can ask Walter if you want to add something about this topic.
Actually, I have a question for you, because, I'm a freshman in the university, in the academia. We are always talking about the Green Chemistry Institute, no? We have been awarded by the Pharmaceutical Roundtable of a grant, etc. Why not an initiative in Europe? So the reference is becoming absolutely United States. In the pharmaceutical roundtable now, all the European company are joining that, and that's fine because sharing information is critical. But why in Europe we didn't do it?
No, you're because that was what I say. We are missing also. I'm leading at the moment the division and group of the Italian Chemical Society in Green Chemistry, and Chiara is here. When we started, I was talking about education as well because it's difficult thing to start. There are some barriers, and I'm just taking this as an example, but Paul can tell us probably it's been a lot of work to go to do this or not. It hasn't been easy, but I think this is a guide and we can give our contribution. We will, I really hope, because it's, should be a joint effort in finding this. Also, to some extent, for example, at least in Italy, the textbooks are American. We are I'm using the American version, but very often our teaching is very inspired by the American system. So that somehow we depend on that. We should develop our way. And you are totally right. Also the UCAM Green Chemistry Division should also do something about this. And
I see that Paul is keen to say something about this.
yes.
I would just suggest that you never have to force anybody to do something that they want to do. And the reason I started off with the eclipse and alignment is because I actually think that at the time, 20 years ago, when I and a great colleague of mine called Buzz Q pulled together the pharmaceutical roundtable, the Green Chemistry Pharmaceutical Roundtable, it was somewhat easy because there were champions in the major pharmaceutical houses that wanted to do this, that saw the value, and they saw the value in different parts of the company as well. All the way from discovery to process to regulatory, and so aligning interests usually lowers that energy barrier and pulling things together like you suggested. The only thing that I would add to your point about tools is that tools including they can be databases or lists or metrics or those tools can sometimes be can either be a reflection of the status quo or the change that you want to see happen. And often innovation and changing the status quo is very uncomfortable. And so many times we fall back on different tools and frameworks that are comfortable for us. And inadvertently, and some of the tools that I see in sustainability, some of the ways that we measure sustainability progress are more a reflection of the past than they are of the future that we want to achieve. So, for instance, I often ask, why would we use the same metrics, models, economic models, business models to get to a different future as we've used to get us into the problems that we've created? So sometimes we need to very significantly change our tools and our ways of measuring progress.
Thank you. So, Fabrizio, do you want to add something?
Just a comment concerning the research carried out in academy and university, and I think that probably it should be driven in some way more by the applied research. What I mean is that sometimes we are carrying out reactions in the lab and we find good results, and then we are proposing to some companies, and then we discover that that solvent cannot be used in the industry because it is too dangerous, because of whichever is the reason. And so in some way it would be important that, especially when the research is just going to be applied, I mean, the aim is that to be applied in industry, there should be some more strict relationship between the industrial company and the public research. This is the first comment. The second comment concerns the education. You're right, Giulia, this is very important. And I'm realizing now that this is really a crucial point. I am participating in a European project together with Paola. And we are chemists and we know very well the meaning of the term bioeconomy. But when we try to explain people who are not chemists, we realize that they have a completely different view of the bioeconomy. So it is important, it is fundamental that there is a sort of common agreement on the meaning of the fundamental meaning of some words, because this then has important implications in research and development. And this has to be done from the very beginning in the primary school and like this, because otherwise this can really give rise to problems, and this is what we are experiencing in this European project.
Yeah, I think, okay, you're right. It's not at the level of university, but high school and also even earlier. Actually, at the moment, we didn't start, but there is some training for future teacher in high school and so on. And at least for us, we decided to give a module on green chemistry for that. It would be difficult because it's not on the contents, but it's on the methodology to apply. But so I don't know how we'll do that. I don't know how, but okay, it will be a important task. But I think it really, that's also, we need to start from the very beginning and also from the people that are teaching. So us and the colleague in high school, it's strategic, it's very, very important. It's one of the major efforts that we have to do.
Thank you, Luigi. You want to add something?
I completely agree with Giulia and Fabrizio about the relevance of education. I agree that this is a very crucial theme. And from my point of view, it is very important that young chemists should be, let me say, formed not only by chemists. So the problem is our world is becoming more and more interconnected, and we need to contaminate each other with different disciplines, different scientific disciplines, maybe also some human disciplines in the formation, in the education of a young chemist. I think that it should be necessary.
Absolutely, it's not okay. It's not only the content, but it's the competence that we give to them. I would say that's the most important things, because okay, the amount of knowledge that you need for chemistry is impossible to give during college or whatever. You need how they learn, and okay, they need to be able to think and to be creative. I would say that's one of the very nice part of our job. Outside, people that are not chemists don't think the chemists are creative, but this is really creativity is, and okay, creativity in order to do something real. So we need to know what is okay for a company, for an industry, industrial process, and what is absolutely not. But that's also why I would say this, what has been done, I was showing, is just put the things in the correct environment, in the correct perspective. So I don't use, I know what solvent can be. I know that, and maybe I don't use dioxane to do my research. I would say I avoid that completely. Thank you.
Just very quickly, for those who may not be familiar, there's a platform, online platform called the Green Chemistry Teaching and Learning Community, and anyone can sign up. And there's a tremendous amount of material, curriculum material, lessons, slides, videos, you name it. And Beyond Benign is a teaching and learning community in green chemistry that goes from, primary school all the way through professional.
Okay, there are questions and issues from the public, from people here.
Yes, I have one. Can I? On education. So I know that this morning will be inspiring, and I thank you because I teach organic chemistry, fundamental organic chemistry in the environmental science course. So I have a lot of examples, cases, and so on to add to my traditional lesson. So this is always an addition for me. I never thought of substituting just from the beginning the fundamental steps. I will think about this. Thank you very much.
We do that, but I think we should put this in the book, in text.
Yes, okay.
So this should be
for sure.
or maybe I have a panel and it just change a little bit because some of them are very, very traditional.
Modern students don't use textbooks so much. So
There are questions there?
Hi, thank you a lot for these interesting talks. But what I wanted to ask is that I like this idea of why stop a positive change because of this shared fantasy of money and whatever. But the thing is that we can all agree here because we are all scientists, we are chemists, more or less. And this is why we are not handling the world's economy, right? So, but you worked with people that kind of do. You work with other kinds of people, with politicians, with lawmakers, whatever, when you were in the White House. So the question that I have is, these people more or less think more short term, maybe they don't believe in these things, the climate change, whatever. So what are their thoughts? Because I guess you proposed some stuff to them. They would have to force corporations to do stuff. What are their thoughts? What are the real problems, the practical problems that make this idea not so viable right now?
Okay, I don't know because it was long. Maybe I lost a part of it. But we say you were talking about obligation. I would say there is no obligation. The thing should be convenient. You should take advantage of what the system gives you. But say you were talking mainly about teaching or research.
No, I'm sorry, I wasn't very clear. This was a direct question directed more to Professor Anastas, but you can all participate in the answer, of course. It's more about how to make this from an idea to a practical solution.
To make it practical.
Something, sorry?
To make it real.
Yeah, because I know that in teachings and in laboratories, maybe we can do some stuff, but this is very small scale stuff. This is a very small scale idea.
Okay, as in research, it's just you try and you see if it works or not. But let's say because the process is very, very long. If you have if you work together, you have input from the other part, maybe what you are proposing or changes is more efficient, or maybe you have better chance to do it. When you decide where maybe for the teaching, for example, certain example shouldn't be there anymore in the book. As a professor, I tell you that the students say, okay, that's the story. I teach you this. Then the next day said, okay, but we don't do this anymore. And so you should think in a different way. If I start telling, okay, I need to understand how reactions are, but I need to do them in a different way, or just to use better catalytic method or other things, of course, this will make a change how you start. And then because in the young people, there is much more creativity and more idea, also maybe with contamination from other fields or other disciplines, then there will be the new solution. Professor Anastas was showing the leaves of the tree. So that finally you have to do something, and this something should be not starting from the very bottom where how I was studying, how I was working 30 years ago, but starting from something already, some steps are there, and I put my effort to go up, not to just to reach the level and then go up. That's my opinion, but okay, I think others can
Well,
give some.
You have been called, so if you want.
Yeah,
to add
yeah, you have
something.
to give much more pertinent.
My father always told me, always speak the language of the tribe that you're talking to. 99.9% of the people in the world are not chemists. We start lecturing them about how to oxidize a hydroxyl group beta-2 a carbonyl. That ain't gonna work. Of all of the successes of green chemistry and science and business and education, we have failed at one big thing: capturing the power of story, making it relevant to everyone. If we want to say that chemistry is fundamental and basic to everyone, then we need to be able to explain to everyone why it's relevant and why it's better and why they should be demanding it. Nobody is going to demand something that they're not aware of. And so if we're speaking to a group of consumers, then we have to speak to their needs. If we're talking to parents, we have to speak to why it's relevant to them. If we're talking to legislatures, if we're talking to business people, if we're talking to environmentalists, we have to speak the language, which means putting it, not changing the facts, just putting it in terms that can be understood. We look at the past 40 years in the failure of climate change communication to explain to people and say, oh, if they only understood the science, if they, those people, if they only understood the science, it wasn't their fault. We needed to explain the relevance in terms that they could understand about how it was going to impact their daily lives, their children, where they lived, their health, the people that they cared about, that it was here, now, happening, and not in the future, somewhere else, to somebody else, and oh, there's nothing we can do about it. No, in that case, just as in the case of green chemistry, it's here, it's now, it's impacting you and the people that you care about, and there's lots that you can do about it. And that's how we have to explain. That's the only way that you can persuade.
Okay, so are there more questions, issues that you want to ask, that you want to raise? If not, okay, it's time to take some rest. We have a coffee break now in the room close to here. So it is about 20 minutes, and then we'll be back to go ahead with our discussion.
Okay, it's time to start again. The first part of this morning has been really interesting. I'm sure it will be the same for the second part. We will start speaking about the greening of the chemical industry, and the introduction to stimulate the debate is from Fabrizio Cavani. Please, Fabrizio.
Thank you, Paola. I will stand on because I'm not able to speak while sitting. Okay, when we are talking about the greening of chemical or the chemical industry, we mean renewables, we mean industrial symbiosis, carbon dioxide sequestration and utilization, regulatory, recycle and reuse, LCA, even with societal and economic implications, alternative energy sources, greener catalysts, water consumption, green solvents, less solvents. I'll try to give an overview about the situation of the European chemical industry. About the European chemical industry in Europe, since 1990, the greenhouse gases emissions have been decreasing by the 50%, especially N2O, but even CO, carbon dioxide, and this clearly is a good news. And specifically, we can see that the chemical production in Europe has been decoupled already starting from the 90s. This is the increase of the production, and these are the corresponding decrease of the greenhouse gases emissions. Which have been the priorities in the chemical industries after the 80s? Energy saving, yes, of course. Replaces there those compounds, reactants, and products, for example, products which have been banned. Replacement of toxic reactants for greener ones. Processes with less inorganic waste, like new technologies for methyl methacrylate, caprolactam, dinitrotoluene. processes with less chlorine input, new technologies for propene oxide, phenol, aniline, epichlorohydrin, TDI, MDDI. However, chlorine is still a problem because over 60 million tons of chlorine are produced, and of the amount which is used in the chemical industry, almost 1/3 of it finally ends up in waste. Processes with a better carbon economy, less carbon loss, for example, processes for maleic anhydride, nicotinic acid, vanillin, change of reaction conditions to limit vent emissions like oxygen instead of air in oxidation processes, reactant rich against versus reactant lean conditions, change of catalyst type, new greener catalysts for oxidation, alkylation, acylation, esterification and deterification, activation of hydrogen peroxide, and finally process integration, for example, hydrogen peroxide generation and utilization, multifunctional catalysts for multi-step but one-pot processes, and byproducts which are used as reactants. These are priorities which have been in the chemical industries up to still used, but especially in the 80s, 90s, at the beginning of the new century. However, there are still some big challenges which are left to solve for bulk chemicals. Again, the use of chlorine. It should be necessary to decrease the use of chlorine for the production of chemicals which do not contain chlorine. A greener process for adipic acid, fewer steps and no nitric acid as an oxidant. The dream reaction of the direct oxidation of benzene to phenol with hydrogen peroxide, and the mother of all the challenges, which is the direct oxidation of methane to methanol, not only to avoid the endothermal steam reforming, but also avoid the flaming of methane of associated gas in offshore plants. I used to say to my students that if anyone will invent the catalyst for this will become rich. Me, I'm not rich, so probably there is wrong for this. Okay, what about today? The European chemical industry was one of the first sectors to support the Green Deal and had the ambition to become climate neutral by 2050. And the CEFIC, which is the European Federation of Chemical Society, is monitoring projects, low carbon projects, renewables instead of petroleum, carbon dioxide sequestration and utilization, e-crackers, steam crackers with electricity, efficiency of technical processes, hydrogen, recycling, mechanical and chemical, renewable and low carbon electricity, and power purchase agreements, waste biomass to energy. Well, if we look at the press releases during the latest 8 months, only concerning biochemicals without considering biofuels or the cycle of plastic and so on, we can find just during the latest month several press releases from different chemical companies about the production of chemicals starting from biomass instead of petroleum, bioparaxylene, propylene glycol, acrylates, butanediol, polyol, acetonitrile, acrylonitrile, biopropylene, ethyl acetate, and so on. So it seems that companies are really willing to develop new technologies, getting rid of petroleum, and this is the very good news. And most of the announcement of the press releases concern the use of renewable feedstock and catalysis, which are number 7 and 9 in the green chemistry principles published by Paul Anastas. But the question here, are the real perspectives so green in the chemical industry? In order to reply to this question, I will start with this article, which was published in the Wall Street Journal a few weeks ago, regarding the talk given by Peter Huntsman, with the CEO and president of Huntsman. Huntsman is a very important US chemical company, but 50% of its business is in Europe. And this talk was given at the World Economic Forum in Davos, Switzerland, in January. The talk was Davos devotees deindustrialize Europe. In the name of green utopia, political leaders are quietly killing vital energy-intensive industries. A few sentences from his talk. Over the past 2 years, dozens of energy-intensive manufacturers of most basic materials, chemicals, steel, ceramics, and so on, have ceased or slowed down production in Europe. because of limits on energy-intensive manufacturing, indeed drove down emissions, and this is the good news, but also began to kill productive industries. And this upstream deindustrialization will spread downstream over time into agriculture, automotive, aerospace, and so on. If Europe won't make what the world needs, the production will go elsewhere. It is environmentally and economically irresponsible for Europe to outsource its energy-intensive industry to countries with weaker regulation, employment laws, and safety standards. And indeed, if you look at the trade balance for the chemical factories, companies in Europe, we see that the trade balance, these green bars, has been decreasing over the latest 2 years. This was due to the Ukrainian war, but in general, this value, which is the positive trade balance, is 20% less for the latest 2 years compared to the previous years. From another perspective, we have the protest of farmers all over Europe who disagree with the EU farming policies, the so-called CAPs, which are the common agricultural policies, because of the cost pressures and the paperwork. And for example, they are protesting against the principle of decreasing pesticides because this will increase the costs of production. So it seems that the situation is not so green. Moreover, if you look at the trend of the raw materials, which are called commodities, we see that the cost for petroleum and for the raw materials for the biorefineries, for developing new technologies from renewables instead of petroleum, indeed are going in a similar way. And this is not good, simply because the optimal would be to have a high cost for petroleum and a low cost for biomass. And when both are so low, no one will invest money to develop new technologies from biomass because of the low cost of petroleum and because the old plants have been completely depreciated, and so there is no incentive for developing something new. And this is the reason why in 2018, when there was such a low cost of petroleum, of everything, of the raw materials, okay, during starting from the 2018, many startups had to close the activity, asked for Chapter 11 in US, got sold. This is the non-exhaustive list. Many had to close simply because the startups, which had developed brand new technologies for the production of chemicals, were no longer able to find investors because investors didn't want to put money on new technologies simply because it was not economically acceptable. And so the question is, which is the real situation in the chemical industry? The picture is not clear, okay, of course. And in order to understand this, I made some interviews to European chemical companies in order to get a more clear picture of what is really occurring. To Syensqo, which is the former Solvay, France, Clariant from Germany, DSM from Holland and Switzerland, Poland from Italy, IFF from Spain, Versalis, which is the main chemical company in Italy. And this is a startup, just to have a complete view. And I had two questions. The first question is, what directions is your company taking to achieve the aim of a better sustainability? And the second question that I put to this company is, which are the main obstacles that hinder the practical application of the principles of bioeconomy and circular economy? Unfortunately, we have no time to go in depth, so I will skip the replies. I received the last one yesterday evening, by the way. There is no time to reply, to show you the replies to the first question, and I will go directly to the second one. Starting from Solvay, now the name is Syensqo. These are the problems which are hindering in some way the development of improving the sustainability. Availability of raw materials with certificates. Enough stock available of recycled or renewable raw materials, market acceptance, including higher price acceptance for some markets. Okay. Then this from Clariant, these are the replies to the second question. Bioeconomy, this is a difficulty to scale up to economic competitiveness. Because, for example, what are needed are small-scale delocalized plants which use local biological sources, and otherwise transport costs will be too high. difficult to scale up due to the fact that the biological raw materials, the biomass, vary in time and space, in composition. The quality is not constant, and everyone knows that for chemical industry, it is fundamental to have a stable supply of raw materials in terms of quality, quantity, and availability. About catalysts, the problem is that with such variation, catalysts very often decrease the stability and deactivate. And moreover, this can be a problem for downstream product purification. Moreover, our problem comes from the law, because, for example, used catalyst is not a byproduct, but it is a waste. And because of this, it is very difficult to recycle and reuse. For example, it is impossible to import used catalyst from China to Europe just because it is considered waste. Okay, by law it cannot be done, while China is the biggest market of catalysts. And moreover, real recycling of catalyst can be a technical and chemical problem. DSM is putting the focus on the costs because for recycling it is necessary to invest money, so it's complex and substantial capital expenditure, a high capex, and this may hinder the implementation of bio-based starting materials. Availability of sustainable biomass, and this is a very important point, not necessarily if you are using a biomass as a raw material, we are making a really more sustainable technology. And it is important to find a balance between the increasing demand of resources and the ongoing efforts in environmental conservation. Point, okay, in our experience, the real obstacles are cost-driven. Why? Because European producers are fighting against imported materials, cheaper and very often with higher carbon footprint than the ones produced in Europe. And so availability and cost of renewables, recycled raw materials, and investment costs can really be a problem. IFF, which is the world leader from Spain, international flavor in production of flavors and fragrances, relatively high LCA value of current processes for alternative raw materials. And this is very important. Again, sometimes starting from renewables instead of petroleum does not mean to make a more sustainable technology. And only LCA, well done, can really say if you are making something which is more sustainable. Cost barrier and sourcing assurance, volume and oversupply of renewables. Versalis, it is necessary, according to Versalis, to work in 3 macro areas: education and awareness. We said just 1 hour ago about this. Economic support and incentives, and the regulatory framework. Finally, the startup, this is the Italian startup, Tomapaint, which is extracting a bioresin from a tomato byproduct, so from the agro industry, a transformation of tomato, which in Italy is very important, for the production of a dye. The problem are that, for example, certification, which is important to enter the market, is very expensive. And this is a problem for these small companies. They have to find investors, of course. And moreover, the market can be potentially very high, but there are sectors which are very difficult to penetrate, being reluctant to any change. Another problem, which to me was unexpected, is about the scale-up of processes. Why? Because indeed, chemical engineering companies do not have experience and know-how for the scale-up of technology starting from biomass. They have experience for starting from petroleum, of course, and building blocks from petroleum, but not from biomass. And this can be a problem. And then clearly important to establish collaboration with some cases it is easier than in other cases. Okay, so I try to sum up the comments from the interviews. For the round table, of course, large companies have access to capitals, but in order to implement a new value chain, need conditions which may facilitate the development. It is not only a matter of infrastructure and logistics, but also of finding the proper way to link the primary production of renewables, agricultural, and this is the reason why I said about protest of farmers, or organic byproducts from food industry, very important in Italy, with the downstream chemical transformation, so develop robust value chains. Secondly, new tools for financing, subsidies from the government, local agreements between chemical companies and farmers. This is what we need. The problem of CapEx, how to face the problem of investment, which strategies, co-location, revamping of abandoned plants, startups with innovative ideas should be supported to increase the TRL of invention and in finding investors. Cheaper and more flexible certification procedures are needed. Thirdly, as it has long been for petrochemicals, it is necessary for the biorefinery to have a guaranteed supply of the raw materials in terms of quality, quantity, and accessibility. And this is fundamental for chemical company. Certification and value chain tracking are now indispensable. Are bio-based building blocks really more sustainable? And moreover, my additional comment is that probably there will be some time where the fossil fuels and the renewables will coexist together, because it's impossible to replace completely fossil fuel with renewables. And so how to manage with the concomitant presence of both types of raw materials. Just final comment concerning where is the chemical industry going? Now the carbon dioxide intensity for the production of primary chemicals, okay, is in Europe, in overall, sorry, is close to 1.3. And more or less it is stable since a few years. It means that every ton of the primary chemical, there is 1.3 tons of carbon dioxide which is emitted. However, in order to fit the European Union net zero scenario to 2050, it is necessary to decrease this value. And to 2030, it will be necessary to decrease from 1.3 to 0.9. And this is really a very challenging topic of aim. And how to achieve this? These are the chemicals, primary chemicals, which are responsible most for the carbon dioxide emission. Okay, these have been already optimized. So how to manage with this? It is necessary, for example, in the case of ammonia, to move to the so-called e-ammonia with the electrolysis of water with green energy to produce hydrogen in order to decrease the environmental impact. For methanol, the same, the e-methanol, or produce methanol starting from renewables. And for the primary other type of chemicals, again, it is important to move from the petroleum to the so-called biochemicals or even recycle. A final comment concerning, again, where is the chemical industry going? About artificial intelligence in chemical manufacturing. Potentially, there are several advantages: minimized energy consumption, improved regulatory compliance, streamlined production processes and scheduling, higher end product quality, zero accident culture with virtual inspection and predictive maintenance, asset optimization toward zero waste strategy. And this is clearly something which is a lot to do with the green chemistry principle. This is the future, but I think that you can also learn a lot from the past. Mario Giacomo Levi, 1945. Thank you.
Okay, so much more than an introduction to the topic, but so many inputs and things to debate. So first of all, I will leave the word to you without an order, and then to the public and who want to comment. You can start for sure.
First of all, thank you so much. That was extremely thoughtful. So I guess my comment would be, you portrayed some, tremendously what's the word I'm looking for? I guess familiar arguments. And I think they really reflect as we were saying earlier, that inertia is the most powerful force in the universe. And it often takes various forms to stop change from happening. So I'll use a rather silly example to illustrate what I mean. If collectively a team were to decide, for various reasons, we need to stop playing basketball and we need to start playing chess, and we agree that this needs to happen. That is what the future needs to be. For the members of the team to say, but I can run very fast, but I'm 7 feet tall, but I can shoot a ball from the 3-point line and sink it most of the time, would be irrelevant, because you're playing chess. You're not playing basketball anymore. So when we say we need to get on a sustainable trajectory, we've changed the game. We've changed the rules of the game. The endeavor can no longer, and I know you know this, very Phil, I'm not, we're no longer, well, I say the rules of the game no longer allow for causing harm with air quality, to have 6 to 9 million deaths a year from air quality that is a direct result from our feedstocks for both our materials and our energy. We're no longer allowed to create the kind of, toxicity, waste, damage, all of that, $11 million a minute subsidies, right? That has to change. So when we use the various metrics that say, oh, well, we don't have a certification, it doesn't meet this return on investment, it doesn't meet, that is the same as saying I'm 7 feet tall and I can shoot a jump shot. So since I could talk for hours about this, I will stop right there and see what you think.
Well, my presentation was aiming at demonstrating the complexity of the problem. Yeah. Okay, and we know which are the fundamentals. And as you said at the beginning, now many of these fundamentals seem to us obvious, but indeed they were not obvious 25 years ago, for example. And we know where to have to go. Okay, but in the middle, from the starting point and the end point, there is a lot to work. There is a lot of work to do. Maybe yes, we have to play chess on this. Okay, try to put together different stakeholders, to put together the economists, especially the politicians and the policymakers, but also the common people who want to understand where the money is going. Okay, because finally the people who are paying by means of taxes, paying the revolution and the evolution. Okay, and then finally there is the chemical industry, which is playing a vital and important role in this. And subsidies have been in Europe have always been given or on the topic of biofuels only and exclusively on this, never on biochemicals. Okay, so it means that there is something which is missing. Okay, there is something in the middle, because of course, if a process costs more, but finally is greener, clearly it has to be greener, of course. There is someone, as I already said at the beginning, who has to pay for this difference. Okay, it cannot be, okay, maybe in part the customers, maybe in part the industry, but we also need something from the European Union, from the government. So we need to increase the acceptability of the concept you need to increase the awareness of the importance of doing chemicals from renewables. Okay. Then clearly what policymakers are saying, okay, but petroleum is 90% going to energy and only 10% go to chemicals. So if biofuels or electricity or whatever will take the place of petroleum for fuels, there will be enough petroleum for making chemicals. Okay, but this means to hide the problem behind the door. So we have to solve the problem from our side, and we know how to do it. So it is a very complex game. I don't have the solution. My aim was just to say that there is a past, there is a present for the chemical industry, and there is a future. Unfortunately, it seems that policymakers are only playing in this chess game for the present, for what is today, and never thinking of what is to be tomorrow. Okay. Because finally the problems will arise. I mean, because if Europe has to get the net zero value for whichever type of production in 2050, clearly problems sooner or later will arise. I don't have a solution, of course, no one has it, but it seems that there is something which is missing in the scenario. Okay, something which is missing.
Okay.
And my complaint is about this, what is missing in the scenario.
Okay, I don't want to cut the discussion at this table, but I guess that we have two important examples of something that can be done in the industry later. So I want to ask the public if there is there is some question about this topic. Okay.
Hello, I would like to ask about what the framework for bioresources is going to look like when these become like relevant in the future, which is going to be pretty near 2030, 2050. And are we not going to follow into the same trap that we always do when we need resources, mass resources, and by that I mean exploitation of other economies, other countries? Because the way I see it, Europe doesn't have as a really big request, but doesn't have a large ability to supply. That's my question.
To whom? Your question is? Okay, who want to answer the question briefly, and then we will pass to other. Okay, it is okay. We take it as a comment and not not as a question. Okay, we can go on. There will be time for other questions at the conclusion, so please keep them in mind. Okay, and now what I think it can be a good examples of something in practice, from the theory to practice. Luigi Capuzzi will introduce this important topic, biochemistry for a green environment and industrial perspective in circular bioeconomy. So the keywords are the same, because Fabrizio told us mainly about bioeconomy and circular economy. Please, Luigi.
Thank you. Thank you so much. I would like to start my introduction with showing you a graph. Please give a look to the graph on the left. It is a work done by some Israeli researchers, not very popular in this moment, that demonstrate that in 2020 the global mass created by mankind equaled all the living biomass, and now probably it surpassed. So in practice, as you can see, biomass produced by nature is more or less stable, starting from 1900. In 1900, the contribute of the anthropogenic mass was more or less 3%. It was still 10% in the 60s, and now is overcome the 100%. So we are inside a phenomenon that is very, very difficult to mitigate and to control. And as a further confirmation, you can see in the right graph that is related to the production, the actual production of plastic materials. Now we are at the level of 500 million tons per year. More than half of this quantity has been produced, of the plastic quantity has been produced in the last 20 years. And this is what the following, the pink part is what we expect in the next decades. So what we need to fight in order to fight with this behavior is something that, and what we need is to decouple growth from the use of reserves, because we do not have enough reserves to sustain this continuous growth of materials, of things that we are producing. So keeping in mind these aspects, a few words about Novamont. Novamont Group is a company with its roots in the Mount Edison schools of material science, and created to pursue the ambitious project to integrate chemistry and agriculture, following the ideas of a visionary entrepreneur like Raul Gardini in the 90s. Since the 90s, Novamont started to work to build a model of sustainable development rooted in local areas, with the soil, water, and their regeneration at its earth. Now, Novamont is a benefit company, B Corp certified, is a leader in the production of bioplastics and in the development of biochemicals and bioproducts of renewable origin. As a dimension, as you can see, we are quite remarkable, even not huge as a company. Very recently, we have been acquired by Versalis, Italy's leading chemical company, with the idea to, let me say, from the point of view of any Versalis, to use our platform to accelerate their transition versus a more sustainable chemistry. In the next slide, I try to explain a bit better what is our model that is based on the fact that biochemicals and bioproducts should be considered the tools to do more with less, because this is the only way that we know to fight against the exponential phenomenon that we are facing now. And in order to do this, we need to rethink growth, avoid the one-to-one substitution of fossil-based materials with renewable. The idea is to use bioproducts to develop a cultural change in order redesigning the way in which materials are produced, consumed, and disposed, stop the degradation and pollution of soil and water by using biodegradable products, specifically for those applications where there is a strong risk of accumulation in the environment, and to avoid the waste of organic matter. Use systemically the approach of life cycle analysis in order to measure the real impact of our action, and cooperate very closely with agriculture and with the retailer, experimenting new solution in green chemistry area or in biochemistry in general, with the idea to giving back, for example, to the soil through using carbon farming practices and using new integrated solution for organic and chemical recycling. More in detail, our model is based on 3 pillars. And this is our meaning for circular bioeconomy. The first one is the industrial pillar, and is based on the reindustrialization of disused sites, very abundant in Italy and in Europe. And we have experienced that disused and no longer competitive production sites can be revamped, injecting in these sites robust doses of innovation. The idea is to develop innovative, sustainable process that can contribute to the decarbonization of the economy, taking advantage of the people and working on the pride of these people in order not to consider these people as a waste, as can unfortunately happen sometimes. The second pillar is the agricultural pillar, the raw material. Raw materials are important, and probably most of the failures of the technology providers that Fabrizio showed showed us a few minutes before are related to the lack of control of raw materials. So the idea is to work very closely with farmers, developing new agricultural value chains with low environmental impact, valorizing marginal lands not in competition with food production, and using new technologies to transform waste and byproducts into new byproducts in new bioproducts. The third one is the commercial one, the products seen as a solution. So products designed to ensure that no persistent substances accumulate in compost, in treated water, in sludge, and products that should be designed to be reused and recycled. The main property that we use for our products, please next slide, is biodegradability. Biodegradability in different environments. You should consider biodegradability not as a property that is important in 100% of application. Well, maybe the contrary. Biodegradability is important only in specific application. For example, is a property needed for all the products that are imagined to work in the soil, like auxiliary product for agriculture with a high risk of dispersion in soil that can create accumulation problems. I think to bioherbicide, to biolubricants, mulch films, biodegradable mulch films, and so on. Biodegradation is important in water for all the products that can accumulate in water and sewage sludges or water treatment plants. For example, in case of non-biodegradable additives for cosmetic and detergents. And biodegradation in composting is important in those applications in which there is a high risk of pollution between food residues and the plastic residues, and the formation of this mixed waste will cause the need to handle this mixed waste in landfills or in incinerator. While on the other hand, using biodegradable plastic, you can divert organic residues from the landfills and putting back into the soil, helping the soil to regenerate, increasing the organic carbon content. And this is probably the most efficient system in order to fight against soil desertification. These properties can be used in different applications. I don't want to emphasize too much. It is not the
the topic of this day. Maybe more interesting is the last, is the next slide. Is the next slide in which we show what are our technologies that we have been able to implement in the last 30 years. You can read this slide from the left to the right. It's perfectly logical. Raw materials from renewables, oleaginous dry crops that can be transformed in renewable raw materials from one side. From the other side, all our activities to use organic fraction of municipal solid waste, agro-industrial waste from different value chain, but also absorbance hygiene products, cellulose that you can valorize, CO2, for example, renewable raw materials that can be transformed by using chemical or biotechnological processes to make a lot of different things. Basically, using a chemical process, we are able to produce, among other products, azelaic acid that combined with butanediol from renewable, obtained by a unique biotech process, we can obtain our polyesters under the trade name Origo B, that mixed with the starch, that is our starting point, our first technology, allow us to produce a range of bioplastics. So from the left to the right, what happened in reality to Novamont is exactly the opposite. So we started from the right, developing one first technology, and then integrating, using commercial materials at the beginning, and then integrating the value chain using different steps, adding different technologies and different competencies to the starting bunch of materials. Only as a curiosity, I would like to show you the last slide. This is a representation of our process to transform vegetable oil in azelaic acid and pelargonic acid, starting from vegetable oil, no derivatives. So atom economy is at least in principle perfect, because we can save all the molecules in the vegetable oil. This is a process that does not use ozone, that is let me say the classical way to make this kind of transformation, but use hydrogen peroxide and air together with catalyst. So we start from renewable, we obtain less toxic product using and products that are perfectly biodegradable. Is a good example of from my point of view of the 12 principles, not the all 12 in the same level for sure, but the 12 principles in practice in a relatively high scale. So thanks to Paul and to Dr. Warner to, let me say, to inspire us to make this kind of activity. Thank you.
And so this is a real example of how things can be done. I will start from the public. There are questions from your part.
Thank you very much. Very nice talk. Maybe I didn't get the point, but regarding your last example, you are telling us that you are using a natural oil and not waste. Is it correct?
Yes.
Yeah, so maybe this is not completely green because we are depleting resources using something that could be used, for example, for food purposes. So what is your comment on that? Thank you in any case for the wonderful work.
Let me say, it is the same aspect that we have to face, for example, for our production of butanediol. So now we are using standard sugar. sugar, so-called third generation sugar. Why? Because second generation sugar is still not available.
Okay.
And if will be available sooner or later, maybe it will be not so cheap. So this is something of very a real aspect that we have to face. As far as concerned vegetable oil, you are perfectly right. We are working to develop our own value chain based on oils that can be harvested in marginal areas. We focused our attention in the past on cardoon oil, with not a big success in terms of oil quantity, but with a big success in order to, let me say, regenerate soil. And so we continue to work on cardoon with this aim, more than obtaining a good quality oil. We are now evaluating different oils. Obviously, we need that these oils need to be available in the right quantities. We cannot wait. So we have to start from standard renewable materials, because we cannot wait that will become available second generation or more evoluted part of this kind of materials.
Yeah, so it's the problem that Professor Cavani already discussed.
Exactly.
Thank you very much.
Thank you. Are there other questions from the audience? Someone else wants to ask? Okay. So if you want to add something, I will. Do you prefer to speak there? Okay. And so our yes, for sure. No.
So I just wanted to say thank you because you inspired me. That I thought that was a very inspirational talk, and one of the things that you pointed out and your question really elucidated is that just because you haven't done everything doesn't mean you haven't done anything, and so I so often hear people saying, "Oh, there's no such thing as green chemistry. There's only greener chemistry." And I kind of look and say, do you really think I hadn't thought of that? And the reason that we call it green chemistry is because we set out this goal of perfection, knowing that you're never going to achieve perfection, but knowing that that's the only way that you're going to constantly be striving, that you're always going to be making steps in that right direction. So in the business of renewables and the bio-based economy, there are many, many ways to do the right things wrong, right? And what green chemistry is all about is saying, how do I do the right things right? So yes, none of us want to compete with food, feed, or land use options when it comes to feedstock. And so you start looking at how do I focus on agricultural waste, timber waste, other types of and ways to do that. So I really appreciated your thoughtfulness about that directionality. And about a year ago or so, I wrote a paper. I had just come out of a plastics conference that was all about banning plastics, especially it was all about banning plastics. And I wrote this paper called "Plastics Aren't Bad, Bad Plastics Are Bad." And the difference between saying plastics are bad and bad plastics are bad is night and day. So just saying we're going to ban plastics without getting to, again, the inherent nature, the character and their life cycle is kind of foolishness. What we care about, what we want to get rid of is hazard and adverse consequence, right? We don't want to get rid of the functionality and the benefits. And so that's where chemists come in. So thank you so very much.
Thank you. And now our last key topic, let's say, which is about a green revolution in the sciences of active ingredients in pharmaceutics. As you know, pharmaceutics is one of the sector that is less, let's say, or it was less greener in the past. So please, Walter.
Can you hear me? Okay. So I put DR, you see, in brackets, because I think it's more like an evolution, not a revolution. Because I think the approach the scientist has in terms of designing processes, etc., is going ahead with the evolution of the culture of the society. And the two things has to go together. Otherwise, we are missing the point. Also because sometimes people think that people in the industry, in the pharma industry are really bad. The industry is taking care about our health, but they want money back. But people that are working in the industry, they are also citizens. And that's the reason why the evolution of the culture is really important. What I see now in terms of developing processes is totally different respect to what I was thinking 30 or 35 years ago. I think all the accident directive that we have in Europe are called Seveso 1, Seveso 2, Seveso 3, and everything goes back to this accident, this disaster that took place in 1976, where ICMESA generate this dioxin that was contaminating the soil. And another, at least for me, important factor is the Bamberg Orta Lake approach. Orta is a lake in the north part of Italy. It's the 7th lake of Italy in terms of extension. And in 1927, the Bamberg company started to produce rayon over there, nylon, and they use a lot of copper salt, and they discharge ammonia and copper sulfate into the lake. And after 1 year was already dead. And if you see, TAPS producers start to put nickel, chromium, and zinc into the lake again. And in 1985, the pH of the lake was 3.9. So everybody knew in the north part of Lombardy that you should not go there and have a bath, of course. And then thanks to the CNR, they start the liming. So they use 10,900 tons of calcium carbonate, and they bring back to 6.97 the pH of the lake. And now you can fish. The level of ammonia went down, the level of metals went down. But if you think about making chemistry with, more abundant metals, you have 900 tons of copper and almost the same of chromium and nickel in the lake bed. Okay, luckily they are not contaminated the water, but they are still there. The water now is very nice. You can go there, and we are talking about 1.3 cubic kilometer of water. Okay, so I was growing up nearby, and that's the reason why in 1977 I decided to join the chemistry degree with the idea to make something that, of course, was, different respect to what was in the past. I enter into the pharma company. At the beginning, I was at the Donegani Institute, where the previous speaker was working as well. And then I joined Farmitalia Laurea. But bring a molecule from the idea to the market is a long way. But here, of course, you have also the production. That's what we are talking about. In terms of modality, you have many modalities. You go from small molecule to monoclonal antibody. And chemists play an important role everywhere, from the small molecule to the way you recover and purify proteins and monoclonal antibody to get back your drug. Where are the sources coming from? We have plants, animal sources. We have, of course, soil. We have fermentation. This is a sponge from the sea, and this is a piece of platinum. Artemisia annua is, I think, in 2015, UU2 got the Nobel Prize for discovering Artemisia annua because it's coming a key component of ACD, artemisinin combined therapy for malaria, that are one of the key. And Sigma Tau developed one of the 3 drugs that are on the on the market, I would say, on the treatment in endemic country, and now is part of Alpha Sigma. That is, I mean, the headquarters is in here in Bologna. VIP means very important pigs, because we use everything about pigs. And in fact, from the intestine of the pig, from the mucosa, we are producing heparin. And 90% of the heparin is produced in China, because at the beginning, the idea was, okay, it's polluting. Yes, 170 tons of mucosa, 30 kilo of heparin. 170 tons, 30 kilo. Now there are companies in Europe that are integrated with the company that are generating the meat of the pigs. They are now bringing back to Europe the production with, of course, a safety and environmental clean approach. We have, of course, material coming from crude oil. This is not the penicillium used for the production of penicillin. Is a penicillin that was discovered in Turin and is used for the production of mycophenolic acid. Actually, the most important production is 7 kilometers far from the center of Turin. This is a sponge in the sea where you can extract trabectedin. It was discovered by a Spanish team, and of course, platinum. You have oxaliplatinum, carboplatinum, etc. But what can really integrate everything and try to get more sustainable production is, of course, the work of chemists. So you cannot expect to have the implementation of sustainable process by using the green chemistry principle by a miracle. Okay? It's only coming from hard work. And the hard work, for me, is really critical in this area, the collaboration between academia and industry. The industry can get, of course, new technology, excellence, recruiting that is quite critical nowadays. But the academia can have better education, real world target. But of course, the environment is so important, because these are the most important words in the industry: environment, health, safety, efficacy, sustainability. And immediately you understand you need a multidisciplinary approach. You need the best of the best to be competitive. At the beginning of your journey, if you have to define a process, you have the design moment, okay? And you can use to go on the right side. This is a picture that we generated for our process on peptides, but is valid anywhere. Or you can use, the sinister side. It's up to you to choose, okay? And if you use the right side, you use the principle of green chemistry as a guide, okay? You have to be always there with those principles on the back. And then, if you are really smart and you know the technology, you can also develop new technology in collaboration with academia. You start your journey, solvent, raw material, use the metrics to guide the entire process, okay? Process intensification is the contact point between chemistry and chemical engineer. And then at the end, you have the production of the active pharmaceutical ingredient. But in the picture, you will always have to put the money. So the money is, for me, part of the design. Why? Because when you talk about money, you talk about the investment in plants, the operational cost, and you have other constraints that are the IP that is in the pharma very important, regulatory impact, and competition. It doesn't matter if your process is nice. It has to be nice and competitive. And to do that, you have to be really at the top in terms of technologies. Of course, this is a very famous breakdown of the waste where you see that solvent and water are the most important part of the waste. And these are the technology. In the industry, people do not care. They're not fond of one technology or the other, but simply they are going to use the best one that fit with the target. The important point is that from the beginning, the target was to design a right process. I am not, in the discussion, there was this, if it's green, is more costly. Well, in the pharma, my experience, if you do the correct design, greener is even cheaper, okay? And we saw that in antibiotics, very simple antibiotics, or very complex molecule, 12 steps oncology product. The important point is really the design and the use of the best technology available, the green matrix to guide the development. And of course, the key point is always the environmental health and safety. Of course, sometimes you have to adapt the principle. In this case, it's a translation guide on the use of, for cross-coupling reaction, where you have to, put more specific translation, like itones and toffee. We talk about catalysis, for example, and low PMI, if you talk about, of course, solvents and prevention of waste, etc. These are, or the temperature. If it's a catalysis, the temperature cannot be 130 degrees. If it is 130 degrees, I turn the page on. For me, it's not catalysis. Why use catalysis and use such a kind of temperature? So making a process development is slightly more sophisticated than the picture. Okay, that is coming from a journal that is not anymore available. It was Chemical Education. And the key point is, of course, to define the process space. But when we talk about process, it's from the beginning to the end. It's not the specific chemical transformation. Because specific mechanochemistry, specific chemical transformation, no solvent, and then you have to use the solvent to recover the product. So if you want to make a good assessment, you have to take into consideration the entire cycle. And then process design, process development, DOE, QBD, PAT. I mean, you have a lot of tools that allow you to have what? To have a production that is under full control. And if you control the process, you can use artificial intelligence to finally optimize and manage the plant. The plant in the future, in most companies already like that, there's no personnel, only computers, only people taking care of the maintenance, and that's it. But of course, you need the full development of the process. You have to know your process even better in terms of mechanism, in terms of every single molecule that is coming out. Because your drug, most of the time, is a tiny amount with respect to the entire chemicals that you are using. Now, and this is related to also part of the discussion we have, sustainable processes. There are companies that are producing inside the drug only the last 3-4 steps. They're using fantastic chemistry. And, okay, where is coming the raw material? The raw material is coming from China. And then who cares about their process? And this is not, for me, the correct approach. And I think that now the transition, especially for the big pharma, is to move from a sustainable process to a sustainable supply chain. They are looking at the way all the suppliers are making the drugs, because sustainability and reliability of the supply chain is also related to the fact that all the starting material, the intermediate, are produced competitively, but using a sustainable or greener approach. Pharmaceutical roundtable. We were talking about this before. This was the picture at the pharmaceutical roundtable started in 2005, the Green Chemistry Institute, 1998. This was the picture of the pharmaceutical roundtable in 2014. 10 years later, these are all the big pharma that are present, almost all of them, okay, from Europe, all over the world. And these are all the companies that are producing or developing or making research for them. Again, all over the world. Okay? And the good things is that we are not talking only about education. We are not talking about sharing, because that was one of the key points of the pharmaceutical roundtable. Sharing experience between all the scientists from different companies, but they are also indicating, you know, which are the main focus, the main target, where they have the problems, okay? And And they are also giving money for basic research based on open science. This is my last slide. No, this is my last slide. Of course, designing a process that is taking care from the beginning of the green chemistry guideline is difficult in the pharma industry. It's difficult because you have a lot of competition, especially if the drug is not anymore under patent, is generic. You have, unfortunately, country where, you know, all the green, all the environmental aspects are not so sophisticated. So you need to take into consideration the cost. And if you do that, my experience is that you are able to design good processes. You have to be a good citizen and a good chemist. And to do that, you need to have ethics and principle. Maybe start with 12 is not so bad. Thank you.
Okay, thank you, Walter, very much. So I ask for your comments if you want. Paul, Fabrizio, as you want, Luigi, Giulia. Your comments, who want to start, and then I will give the.
So first of all, thank you. That was really a wonderful summary. One of the things that I thought was came out is because of the complexity of pharmaceutical science, it necessarily lends itself to more opportunities. So if you just think of, you know, a large-scale industrial commodity chemical that takes 2 steps, 3 steps, you have limited flexibility in terms of where you're going to be able to intervene in the overall process. You have 12 steps, you have 23 steps. You just have so much more capability, because getting from target to from starting material to target, you know, you have in the 2-step process, oh, you might have a dozen different ways to get there. 23-step process, you can't imagine how many, what it's, it would probably be close to 10 to the 23rd, I'm exaggerating. But the whole point is opportunity for improvement and intervention and rethinking how not just the synthesis, but the separation and everything else can improve it. So the flip side of that, you know, hopeful and opportunistic perspective is that before we were doing things with, you know, sustainability vision, when we were optimizing for, I'll just say, the wrong things, that we've done things so wrong for so long, we've got nothing but opportunity. So it is exciting to say, I know that when I look at almost any historical process, that I'm going to find ways of improving not only the effectiveness of the process, but also the bottom line. And that is in many ways where the progenitor of the Green Chemistry Pharmaceutical Roundtable came from. And it came from Pfizer, because in the 90s, there was a champion named Buzz Q at Pfizer, and he would brief his boss on all the things they were doing in green chemistry. And there was a party held by the CEO of Pfizer, and the CEO was holding this party because the legal team had just won a big legal challenge, and they won $96 million on some kind of patent fight. So there's this party, and CEO turns to the head of R&D and he said, "Isn't this wonderful, what we've been able to do?" And he said, "You know, I've changed, in one case, just one step on one drug and one process using green chemistry, and I saved you not only over $100 million, but that $100 million is going to be saved every year into the future." that is when the CEO turned the ship and invested very heavily into green chemistry, and it started really cascading. So I just think that there's so many good news stories using new chemistry, elegant chemistry throughout the pharmaceutical industry, and the lessons to be learned there are just wonderful. So thank you so much.
Thank you. Fabrizio, Luigi, Giulia, do you want to add something? Okay, yes, no. And from the audience, this is your last possibility, more or less, to ask questions. Okay, we are in time.
Yes,
So
we are in that. No one want to ask some question in the moment? Okay, we are in time.
okay, we are in time.
So now I'm very happy. I thank you all for this event that has been successful, in my opinion. We have a lot of inspiration. We could deepen for probably 1 week symposium, but we don't have such a time. I'm asking to everybody also online if there is some question that you want to make on the whole topics that we have seen today, to our panelists or to some of them individually, if you prefer. Do you have something that you want to add more? Okay, so now remember that at the end of this morning, we have a buffet lunch at the Department of Chemistry, the old building of the Department of Chemistry. We have a new one, you will see on Thursday, the new one, but we have also still the old building, and there is a lunch buffet there. You are all invited to be there. Before thinking later our panelists, I give the word to Paul, if you want to draw some conclusion remarks about this morning.
Well, I think I'll finish where I started by saying thank you, and that it's been such an honor to be with my fellow panelists, as well as with all of you. When I think about the fact that for whatever reason, a tiny sliver of the population of this world has been given the gift, and yes, I say the gift, of being able to not only understand chemistry, not only being able to understand the molecular world as it is, but to manipulate matter itself, to create things that the universe has never seen before. That is an immense power, to create things, materials, energy storage, whatever it is. A power that very few people have. And with all power comes responsibility. Because we have the power to manipulate matter, to introduce new substances that the world has never seen, I believe that we have the responsibility to use that power for good and never for evil. And once you have an awareness of the consequences, including the adverse consequences that could happen, the idea of saying, oh, well, I know I could do something beneficial, but I'm going to choose not to. That no longer becomes a choice. That no longer becomes a choice if you want to be an ethical person who wants the admiration of your children. Because I have to suggest that any of us who seek the praise or admiration of our peers or our colleagues or our boss or our mentor, we're seeking it from the wrong place. We should desperately care about the admiration and the gratitude of our grandchildren and future generations. That's who we should be seeking, their admiration. Thank you.
So, thank you all. Thank Paola. Thanks Luigi. Thanks Fabrizio. Thanks Paul. Thanks Walter. Thanks Giulia. It is really a nice event that we had, and we want to thank you again for being here. So we finish now, and we move together to the Department of Chemistry. Most of you know where it is, and some not, but we'll go together. Oh, sorry, at the end of the lunch, for those that want to see, there is a short visit to the Museum of Palazzo Poggi, a guided tour in English for Paul and for the others that want to join.